Welcome back to this new clip in the module on geothermal energy. Our focus is now on low temperature geothermal systems. Low temperature systems tap in aquifers with waters at temperatures around 60 to 150 degrees, which are used for heating. Heat cannot be transported very far, and therefore the development of low temperature systems is largely conditioned and driven by the location of the heat demand. Low temperature systems are not very well known to the general public, but because they do not require particular thermal conditions, they have huge potential. In fact, the installed capacity of a heat production geothermal system is more than 6.5 times higher than that of geothermal electricity. Low temperature geothermal systems require permeable rocks, which are called aquifers, with hot enough waters at accessible depths. In the map, you see the maximum temperatures in aquifers in the uppermost 3 kilometers of the crust. If you exclude areas such as mountains and zones of outcropping basement, you can easily conclude that in very large parts of the world, aquifers exist which can be exploited for low temperature geothermal heat production. Let us see now in some more detail how low temperature geothermal systems work. Note that this is quite different from hydrocarbon systems. The first key component is a layer of permeable rocks bounded by less permeable lithologies. We call the first ones aquifers and the second aquiters or cap rocks. As we already seen, rocks can be permeable because of their high primary porosity, like many sandstones, or because of widespread fracture networks. In this case, for instance, the geothermal in southern Germany, where the aquifer is composed of fractured, often karstified carbonates. The aquifer contains water, which will be at the same temperature of the country rock. Through a production well, hot water is pumped to the surface and sent to a heat exchanger where the heat is extracted and distributed to the end user. To replenish the aquifer and prolongate the life of the geothermal system, waters from the heat exchanger are pumped back into the aquifer through the injection well. The cold water flows downward, driven by its higher density, is gradually heated up and eventually reaches the production well where it is pumped back to the heat exchanger. In this way, the volume of the system remains constant, thereby also avoiding pressure changes. A key parameter to assess the economics of low temperature geothermal system is the performance coefficient, which is the ratio between the energy needed to run the system and the heat extracted. This parameter needs to optimize because higher flow rates result in higher heat production, but also in higher energy needed to pump the water in and out of the aquifer. A further key parameter is the lifetime of the system, which is the number of years needed for temperatures at the producer well to decrease below a certain value. This depends on the flow rate at which we operate. If rates are very low, then the water will have ample time to equilibrate with the country rocks and temperatures at the production will not change. If on the contrary rates are high, then an equilibration will be incomplete and temperatures at the production well will decrease. It is generally considered that the low temperature geothermal system become non-economical when the water at the producer has become 5 to 10 degrees cooler than at the beginning of exploitation. Geothermal systems are typically designed to have a lifetime of 20 to 30 years to ensure economic profitability and longevity of heat supply. Finding the best balance requires good understanding of the aquifer properties and good modeling work. In this series of numerical simulation, we show how the geothermal system behaves. Our simplified system is composed of a fully homogeneous aquifer sandwiched between two aquitars. In the slide, you can see a vertical section through the system and a map view at the middle of the aquifer. The plot at the bottom of the slide indicates the temperatures at the production well as a function of time. At time 0, where the water is at 80 degrees and starts being pumped to the surface through the production well. After having released heat and therefore cooled down, it is re-injected into the aquifer. After 10 years, a substantial area around the injector has cooled down, but the cold water front has not reached the production well yet, and water temperatures is unchanged. After 30 years, the cold domain around the injector has extended so much the temperature at the producer starts to decrease. The map view image note that the teardrop shape of the cold front, which is associated with the suction determined by the producer well. After 50 years, the cold front has reached the producer well, where temperatures are now substantially lower, around 70 degrees. In the time versus temperature plot, you can see that if we're willing to accept the temperature decrease to 75 degrees, then the lifetime of the system will be about 37 years. As we've mentioned, flow rate is a key parameter in flow temperature geothermal systems. The two maps show the position of the cold water front after 20 years for two different flow rates. The cool volume is clearly larger in the case of high flow rate. This translates in different lifetimes, around 37 years in the case of 300 meter cube per hour, and much longer for lower flow rate. Large amounts of power can be produced in the high flow rate case, but only for about 20 years. If the decision is made to operate at lower flow rates, the amount of power is substantially less, but spread over a much larger interval of time. Here we present the relevant equations underlying the behavior shown in the previous slides. The energy stored in the aquifer is the heat in place. This depends on the volume of the reservoir, the temperature of the reservoir and of the injected water, and lastly, on the volumetric heat capacity of the rock fluid system. How much of this heat can be extracted depends on the product of the fluid heat capacity times its density, the temperature difference between the produced and the injected water, and the flow rate. Different from what assumed until now, aquifers are not homogeneous and are characterized by a variety of heterogeneities at different scales from the centimeters to the hundreds of meters. Some heterogeneities are associated with lateral changes in type of sediments. The two sand bodies shown in the picture, for instance, are separated by clay layers and therefore do not communicate with each other. Faults are another type of heterogeneity. They can form barriers for the lateral flow of fluids, and if they are not identified correctly, injector and producer wells placed on the two sides of a fault might not communicate. But faults can also channelize fluid flow. This is especially true when faults are associated with thick damages. In some geothermal fields, wells are drilled across faults in order to capture the largest flow of hot water. Predicting the spatial distribution of the heterogeneities is a key task of the geologist working on low-temperature geothermal system. The spatial distribution of the geological heterogeneity depends on the environment in which the sediments were deposited. In meandering river systems, for instance, permeable sands are mainly limited to the channel and pass lateral to the less permeable silts and shales deposited in the floodplains. With time, the river channels migrate laterally, creating a three-dimensional network of sand bodies. In the first step, a geological model of the target volume is built, integrate data from wells with sedimentological knowledge of the relevant sedimentary system. In the second step, physical properties such as permeability and heat capacity are assigned to the different sedimentary bodies forming the model. The model is then ready and is used for a large number of simulations. These include testing the position of the injector and producer wells with respect to the sedimentological heterogeneities and identifying the best distance between these wells. We would like to conclude this clip mentioning some of the challenges facing low-temperature geothermal systems. At the technical level, a significant problem is encountered in several projects is clogging. This is the deposition of minerals such as calcite inside the well and pipes, resulting in the decrease of the production capacity. Clogging can be dealt with by adding chemicals which inhibit the precipitation of calcite. Other challenges are associated with the pressure changes which might take place in the aquifer when fluids are injected to increase aquifer permeability. If not carefully predicted and monitored, pressure changes can cause fault slip and other unwanted side effects. Low-temperature geothermal energy has surely a great potential. It is attractive for a large number of countries and regions throughout the world, and it will become increasingly important. The economics of these systems can be challenging, and successful exploitation requires an excellent aquifer and a large amount of customers very close to the well. In fact, The well is placed there where the customers are. Permeability can form a challenge, especially because of processes around the borehole. There are, however, various stimulation techniques which can help. Modeling and monitoring are of key importance in order to have a long enough lifetime. Plenty of opportunity ahead of us.